right, so next talk. So Finn will tell us about linking implementation with their verified designs.
All right, thank you for your introduction. So let's talk about trace validation. First of all, just to set our basics, distributed systems are well known to be really confusing to deal with. Concurrency makes sure you don't know quite what order things happened in. Partial failure makes sure that you're not sure how much of your system might necessarily be running. And network semantics makes sure that you're not quite sure when or how many of any given message gets received. TLA Plus is one of quite a few ways of trying to cope with all of this confusion. How does it help exactly? Well, it's an abstract modeling tool, and it allows you to describe your system as a kind of set theoretic state machine kind of description with various high-level mathematical abstractions, which you can then model check and verify against properties to see if it does what you think. It's had some degree of adoption in industrial projects, and some big systems have specifications in it. But there's no real link to their actual implementations, which are usually carefully engineered, C++, Java, or something, but not particularly related to your TLA Plus specification at all. One way to deal with this lack of relationship, which can obviously lead to all sorts of desynchronizations, is trace validation, which is a TLA Plus land technique that has had some degree of development over the last few years and some industrial successes. What is it? It's a way of taking logs from running your handwritten implementation and describing a formal relationship between events in the logs and what your specification actually says in terms of state variables and actions. And then you can use a model checker to resolve the ambiguities in information that is not in the log, ambiguities in the formal relationship you described between log and specification, and ambiguities in the specification, all of which you can tolerate to some extent by using a model checker to solve for those things. Now, this is just the state of the art. That's already a thing that you can do. But all of this existing work uses manual setup and instrumentation. So you have to go in and actually add all the logs to your system. You have to write this relationship by hand also. It may be relatively boilerplatey, but you have to do it. And that's, like, fine, but can we do better? Well, in this strange circumstance we have, where we are authors of Pigo, a specification compiler that goes from TLA Plus compatible specifications to generated implementations, we own the entire compilation process and can therefore add much more precise and detailed instrumentation than would normally be reasonable. And we can do all of this automatically while preserving all of these relationships and generating all the stuff. So essentially what we've done is we've automated the process of trace validation for our specification compiler. Here is its architecture diagram, and essentially what we have is modular pluscal, which is our addition to, it's a TLA Plus compatible modeling language, which you can then extract TLA Plus from and generate into Go programs that will then run. What we added to it to make TraceLink, which is our project, is all of this. So we have Go instrumentation, which inserts itself into the implementation code and records a very detailed trace of what happened. And then we have the TraceLink process, which takes the trace and metadata from the specification to generate a complete relationship mapping the trace onto the formal specification, which we may then model check using an out-of-the-box model checker for TLA Plus. And you might think I'm about to tell you how all the Pigo instrumentation and all that works, but actually I won't. I'm going to talk to you about a very specific and interesting detail of how we get to do trace validation that is different from all other trace validation because of the high detail instrumentation we have access to. So let's talk about this trace validation variation. First, I'll tell you about a really, really simple distributed system, just for illustration purposes. Imagine we have a global variable x, which is accessed by Alice and Bob. Alice and Bob may increment x. Very exciting operation, I know. To share x, Alice and Bob will exchange UDP messages. And of course, global variable x being shared is a complete lie, Alice and Bob have local copies of X, and it's up to them to keep them in sync correctly. That's why this is a very slightly interesting distributed system. Now, what I want to get at here is, in all prior work on trace validation, what they're validating is a pre-sorted trace. So what we mean by this is we take the log of all the nodes of your system, merge it, sort by timestamp, and we have a complete global order of everything we think happened. Now let me show you an example of something that could result from this. So we have our initial value of X, which is 0, and then Alice increments from 0 to 1. Then Alice sends a copy of X to Bob. Alice increments X from 1 to 2. Bob increments X from 2 to 3. I know some of you might have just noticed something very strange here. And then Bob receives X from Alice. Now, you might think, OK, this is obviously wrong. That's the wrong way around. But let's take a step back and think about what kind of formal specification we might be validating against. And I will introduce my one little contrived example here. So the spec we're using is X may always increment by 1. X does not go down. And we just view X as a global here. And also, Alice sends X to Bob. This is the actual specification of what is allowed to happen. But in this example, Bob is clearly psychic and has seen something that Bob is not supposed to see. So what's the deal here? Technically, this would be accepted by this slightly lax specification. And for the TLA plus experts, there's a little small print at the bottom, but basically, trust me that this is a real omission you can make in TLA plus. You can do all sorts of abstractions and simplifications about things you don't want to talk about, and you might accidentally omit something like the causal relationship between synchronizing X and actually incrementing it so that you would actually accept this entire series of events. OK, that's kind of annoying and unsatisfying. What could we possibly do about it? Well, remember I was talking about pre-sorted traces. We get to instrument our system using vector clocks and store causal traces instead. So I'm not going to explain what vector clocks are, but understand that formally, this gives us a partial order that actually maps causally who exchanged what information at what time. And as a result, we can recreate our trace, but now with a bit of a partial order flair. So Alice has incremented from 0 to 1. Alice sends X to Bob. Alice increments from 1 to 2. And actually, at any point, Bob could have incremented from 2 to 3. That seems a lot more problematic now, even with our very lax standards. And also, Bob can receive X from Alex after Alice sent it. OK, cool. And now we can see the deeply problematic nature of my original example, now that you can actually see the causal traces rather than just a sorted example of it. And this is something we'd be able to detect even without changing anything about our specification. So just to get into this, when you're dealing with causality, you can have multiple interpretations of your trace. Here are some of them. This one, Bob was considered to have incremented X before Alice incremented it, and that's a validation failure. Here's another one that just permutes a couple of them, but is still obviously a validation failure. And here's our original example, which is still possible. So we want to not actually only validate this last one, because if we validate that, if we just pick this trace, then we still pass it, and we don't want to pass this because there's something obviously very wrong with this system. This gets into the practicalities of actually model checking these things, because we say we have a model checker to solve ambiguities. We are now solving ambiguities of which trace to choose. And we basically get depth-first search, so we pick any one path, roughly speaking, or breadth-first search, pick all the paths. And I don't want to check every path. So we tried doing this, and on one single example, we had to kill the process after 12 hours. It does not work. So we seem to be stuck with one path, but that's completely impractical. So we have this strategy called sidestep, which is essentially we pick one path, and imagine we do get unlucky and we pick the path that would have validated. But for every step of the path, we validate the alternative schedule by one step only. So for every alternative path each step, just one point of it. And what this gives us is a complexity, give or take a constant factor, comparable to single path, which means when we run it, it doesn't take all day. It takes a few minutes. And here, bonus, we can actually find that Bob's incorrect increment is visible even in the initial state. So we can get a really short counterexample to our model checking. Of course, as long as it's findable in one step. This is not a perfect technique, but it's better than all day versus get unlucky even in this case. So there are a lot of other details in our paper that you can check out. And for example, there's how Pigo is instrumented. There's the complete formal semantics of our translation. There's 9 bugs that I will try to talk about maybe one of. And there's a compression scheme for our generated TLA+, which is normally very big. So our evaluation of this technique and automation process focuses on 3 systems built with Pigo, because we rely on the Pigo compiler to do all of our instrumentation. The main one of interest is called Raft KVS, which is a Raft-based key-value store. It's a pretty complex system which was built for performance benchmarking and stuff, so it has a lot of fun tricks and is representative relatively of real software. We got log sizes of up to 100,000 events across 26 processes, and some of our counterexamples were over 10,000 states deep. A rough list of the bugs that we found are in some interesting categories. There were wrong specification assumptions, there was one miscompilation in Pigo, and various mismatches in terms of modeling trade-offs. I will tell you a tiny bit about one of them, because that's all I have time for. And that was when we accidentally modeled TCP incorrectly. Essentially, it's not that we did anything strictly wrong in terms of what TCP allows, but rather we over-strengthened its sequencing properties such that we required all TCP connections to the same recipient to be globally sequenced to each other. Again, this is just a little thing where you omit something in TLA+, and you have a very strange counterintuitive consequence come out of it. And we were able to detect this, catch it, triage it, etc., using TraceLink. The other thing that we evaluated was the effectiveness of sidestep. And I won't get into it too much, but it turns out it doesn't change the ability to find bugs very much, but it changes the length of our allowed counterexamples by a great deal. So, for example, it decreased the counterexample length by 11,000 states. Now remember, a human has to actually read and review these states in some way, even with Control-F. So I'm very happy that it makes these a lot shorter. It helps immensely with triage. And sometimes it makes your model checking a lot faster as well. In summary, that's basically all I had time to tell you about. We have a push-button validation system for Pigo. Feel free to ask me for details. We have this causal-aware validation and sidestep technique, which I think is interesting and I've spent most of my time telling you about. We found 9 bugs in the Pigo context, and you're welcome to ask me more about those. Our ongoing work is about trying to reduce the reliance on Pigo and apply to other systems, especially applying this causal validation techniques to handwritten code. Also, I'll be graduating soon, so if you have any job opportunities, that would be great. Thank you very much.
All right. Questions? So are you aware of the work on conformance testing?
Yes, in conversations, I call this conformance testing to some extent, though I might not know the example you mean. Is there?
So for conformance testing, imagine I have a state machine like your TLA specification. I will generate inputs and then get output back to check whether I'm in the expected state or not. And I keep doing this, traversing the state machine. And then if I have reached a state where I'm not supposed to be next state, I will report it back, kind of, sort of.
Okay.
I'm wondering if you, how do you compare in terms of performance? And the way I see this is if you do conformance testing, you have to cut up your system into 2 pieces. It's almost like client server. You have a state machine of the other part, and you act as another subpart, and you interact with it to see whether you conform it. But for you, you do a monolithic trace modeling.
Yeah, with all the pieces instrumented, yes.
Yeah.
So I would say the key difference here is, in this case, we focus on solving for partial or ambiguous inputs or results. So if you have, for example, you're not sure the order you did things in, or you're not sure exactly what the value of variables were, this has abilities to tolerate and solve for those, whereas perhaps normal conformance testing is more of a strictly instrumented setup where you control the inputs and then look at the outputs.
Yeah.
I haven't actually tested any performance comparisons with this, but that is interesting. I should look into it. Thank you.
Yeah, all right. Thanks, speaker, again.